Welcome to the Jack Westin MCAT podcast with your host, Phil Hawkins.
And Azaii Calderon Muñiz.
Phil, I'm not feeling quite as connected. There's just the force between us. It's not the same. Is it time that we split up? Do we need to separate?
I did not know where you were going with that.
Today we are talking about nuclear physics. So we are going to be talking about protons, neutrons, what keeps them together, what allows them to separate. And so don't worry, you guys. Phil and I, the podcast, we are not splitting up. We are not separating. But we'll talk about how atoms can and how nucleons or neutrons and protons can split up.
Yeah, this is, I feel like when people hear, oh, this is the nuclear physics episode, everyone's going to be like, oh my God, like this is going to get real deep real fast.
But it's us.
Yeah, nuclear physics is not as difficult as it seems at first glance. I feel like that is a very egotistical sentence. If I heard somebody else say like, oh, nuclear physics, it's no big deal. I'm like, okay, there is some tricky stuff going on here, but it's not as bad as I think most students think it's going to be.
Okay, so yes, because you're a very physics person, but I'm not a physics person. So if I can follow along and I fear physics, we'll make sure that you guys can follow along and that we demystify the madness.
Yeah. So we should talk about the nucleus, right? Like, what is a nucleus? Obviously, it's made of protons and neutrons. There's some weird stuff kind of going on as we go through this. Like a lot of students, when they learn about electrostatics, right? Like positive charges repel each other. So like if you had a bunch of positive charges and neutral charges together in a ball, like the positive charges want to get away from each other. And that's true. Generally, protons are going to repel each other, but there are different types of energy, like nuclear binding energy that's used to kind of like help hold these things together. And we're going to talk more about this as we kind of go out through the lecture. But every atom is a mixture of protons and neutrons, with the exception of hydrogen, where it's just a proton most of the time in its nucleus. But we have these mixtures of protons and neutrons, and some of them are more stable than others. Some of them are like a more stable nuclei. And so, thinking about terms of energy, right? We talk about this in chemistry a lot. Like something that is more stable is lower energy. Something that's unstable is higher energy. So as we go from like a high energy thing to a low energy, as we go from an unstable thing to a stable thing, that's going to release energy. And this is where nuclear energy comes in, which we're also going to be talking about today, and nuclear bombs. And there's just like a lot of really interesting things in like the real world that are related to this stuff. And so it is actually, I think, something that I feel like every human should try to get an understanding of like what is going on with like nuclear physics. So like just a brief overview, because it's kind of important for the understanding of real world stuff in terms of like politics and understanding energy problems and energy crises and things like that.
Yeah, my brother, I think I've mentioned this to you before. My brother is super interested in nuclear energy. And every so often, he'll just start talking about it. And I'm like, okay, cool. And so, there are times where I wish I understood what he was talking about when he would first bring it up. And now I'm just like, I kind of get this. I can dig this. I can follow along. But like you said, it ultimately comes down to neutrons, protons, and atoms, their nucleus, they want to be stable. There needs to be some kind of balance in the system. And anything that causes the slightest bit of instability will make that format, that setup less likely to stay that way, right? Because we are always seeking the lowest energy state. That is why after a run, you will sit down, you will chill. You're not going to start, you don't run and then go for another marathon. I know marathons come up frequently in our conversations.
Yeah.
But in order to find that balance, when an atom is smaller, so generally the first few rows of the periodic table, it wants basically like a 1-to-1 balance. The protons and the neutrons should match. At the end of the day, there are two main kind of forces at play at the level of the nucleus. Like you said, the protons are repelling each other at the level of electrostatics. And then there's also, we're not going to go deep into it. We weren't planning to, but like the strong force that holds these things together. And so you have to have a way to balance the force pulling in and the force pushing away. And so in that 1-to-1, we can use carbon as an example, because a lot of people recognize, oh, carbon is 12 versus carbon 14 is used as well. So in carbon 14, it's still going to have, right, 6 protons, because the number of protons determines the identity of the element. So regardless of whether it's carbon 12 or carbon 14, carbon has 6 protons. What changes the atomic mass then is going to be the number of neutrons, or the mass number is the number of neutrons. And so in carbon 14, it has 8 neutrons, and in carbon 12, it has 6. But if we do the math, we think about the ratio, 8 to 6 versus 6 to 6, 6 to 6 is a ratio of 1. They are balanced. And so that's going to be favorable. That's going to be more stable. So that's why carbon 14 is less stable than carbon 12. And we can have decay, which we're not going to talk about decay today, but we might have to do a whole other podcast on it because there's so many things we could talk about there.
Yeah, for sure. But this is important because the MCAT will ask students like which of these isotopes is most likely to decay. Which of these isotopes is most stable, right? And generally, for especially those first couple of rows of, like oxygen, carbon, helium, fluorine, chlorine, those sorts of things, we want like a 1-to-1 ratio. As we get bigger, into like things like Einsteinium and uranium and terbium and like the crazy elements that are way heavier, generally you start to have more neutrons and it starts to get a little bit less balanced. The MCAT probably is not going to ask you a question about that though, in terms of recognizing which one's stable and which one's unstable. For like the really large things, they're probably going to ask about like carbon, nitrogen, oxygen. And I realized I said the term isotope, and I probably should have clarified that. So carbon 12 and carbon 14 are isotopes of each other. They are like carbon has multiple isotopes, just weighs different amounts, and that's done by adding and removing neutrons. If you add a neutron to carbon 12, it becomes carbon 13. You add another neutron, it becomes carbon 14. If you add a proton to carbon, it becomes nitrogen. It's not carbon anymore. And so the proton determines the actual element. And so there is this balance of like protons to neutrons that's most stable. But there's also like a certain amount of things in the nucleus itself that is more stable. And for some reason, and don't ask me why, because I don't know why, the most stable nucleus overall in terms of size is iron. So anything smaller than iron kind of is less stable than iron is. And anything bigger than iron is also less stable than iron is, right? If you have like a graph of like the atomic mass number and stability, like iron is the most stable. And like once you go like smaller than that, it becomes less stable, and bigger than that, it becomes less stable. And so this is where we start to have some interesting things occurring with like nuclear physics, right? Because when we think about things like stability, right? Stability is lower energy. Something unstable is higher energy. And so if iron is super stable and everything smaller and everything larger is less stable, then that means all of those things are higher energy. And so like nuclei kind of want to become iron because that's the most stable thing. And so if I have hydrogens, which are really small, like if I take 2 hydrogens and smash them together, make helium, like that is going to be more stable because it's getting closer to iron because it's getting bigger, right? If I take really big things like uranium and I break that into smaller pieces, right, that's going to be more stable because it's getting closer to iron. So in terms of this, like the really big stuff, we kind of want to break it into smaller pieces. And the really small stuff, we kind of want to smash them together to make bigger things because we want to make things that are closer to iron overall. And this is a lot of what's happening in like nuclear reactions, is like combining small things or breaking apart big things. And this is where nuclear fusion and nuclear fission come in.
So starting off with nuclear fission. So I think this is the one that makes, at least for me, more intuitive sense because, like you said, it wants to get to the level of iron. And so it wants to break down. And when it breaks down, it's going to produce energy. So essentially what's happening in fission, you have this neutron come slamming in to an unstable element, right? And that unstable element is going to start breaking apart. And we just said that would release energy, right? And then the neutrons, not the nucleus, the neutrons that then go flying into other nuclei, right, and into other elements are going to continue breaking down. And so with nuclear fission, it's actually, I say fairly easy, but fairly easy to start because once it starts, it's going to just keep going. And so you're able to consistently produce higher amounts of energy. And this is the bigger you start, great, because you have all this extra energy. And so uranium is one of the elements that's primarily used when you're releasing energy and producing energy using nuclear physics, specifically nuclear fission.
Yeah. And this is so fizzing or fission is when things are getting smaller. Fusion is smashing them together. So nuclear fission, if we're going from uranium, which is less stable, to iron, which is more stable, or getting closer to iron because we're getting smaller, like that's going to be going to a lower energy state. But energy can't be created or destroyed, right? So like if we're going from high energy to low energy, what happens to that leftover energy? Well, that's just released. And this is what happens in nuclear bombs, like uranium bombs. This is what happens in nuclear reactors, right? We're releasing tons of energy from just this cascade. And when a uranium breaks down, it releases neutrons and those hit other ones and those break down and release even more neutrons. So we have this kind of like cascading scenario. And obviously this releases a ton of energy, right? Like nuclear bombs are the most powerful bombs that we have created as humanity. Like they make like TNT seem like nothing, right? Like it makes it look like a firecracker in comparison. And so this is a big deal, right? This like fission reaction. The thing is, uranium's kind of rare in the environment, right? Especially like the particularly unstable isotopes of uranium that we can that we can kind of like get to react because like we have to put in some energy to overcome the activation energy. They don't require that much to get them to start to go and like set off this reaction. And so it's pretty rare. And so like you have to mine it and you have to purify it, enrich it, which is like, getting like the right ratio of like atoms in there. And it's something that can create this cascade. Because if you don't have much uranium, like one will break apart, release those neutrons that'll just hit other stuff that isn't uranium. And then like nothing will happen. And like there's not going to be much energy released. But it would, I think the two forms of nuclear reactions that students are likely to come across in the world. One is like uranium, like understanding what's going on with that. Also plutonium, similar thing, right? Plutonium's also very large. So it's a fission reaction. But you can also have this happen in the other direction, right? If we have some really small stuff and we combine them, that's fusion. And that also releases a ton of energy. And so fusion, like where does this come from in our everyday life, right? Well, the sun, right? Yeah, exactly. The sun is made of hydrogen, which fuses to become helium. There's a song by the band They Might Be Giants. I always think it whenever I think about this. I don't know if you're familiar with it, Azaii.
The band definitely rings a bell. I'm gonna have to look up this song.
Yeah, well, you're in luck because I'm gonna sing it. There's like there's a set of lyrics in there like the sun is a massive incandescent gas, a gigantic nuclear furnace where hydrogen is fused into helium at a temperature of millions of degrees. It's a great song that I always think about whenever I think about nuclear reactions. But that's exactly what's happening. Like hydrogen is combining to form helium, and that releases a ton of energy. That energy is released in the form of light that makes it to the earth, and plants use that to make carbohydrates with photosynthesis, and animals eat that, and then we eat the animals and we eat the plants. And so like all the energy that we have is coming from this. Even like if you think about like gasoline and like coal and stuff like that, those are plants that grew based on sunlight, and then they got compressed, and like dinosaurs and plants got kind of compressed until they turned into oil and coal. And so those things are also like that energy actually comes from the sun as well. So all the energy that we use in the world is pretty much coming from the sun at some point. Now, the thing with hydrogen and this fusion reaction is this is kind of the opposite of the uranium thing, right? Uranium is rare, but it's fairly easy to set off, right? Hydrogen is super common. And when I say super common, I mean like it is the most abundant element in the universe by far. It's the most abundant element on Earth. It's the most abundant element in you. Like people are mostly water, and water is 2 parts hydrogen to 1 part oxygen. And so I'm like, the oceans are 2/3 hydrogen. And so we don't have any shortage of hydrogen, right? Hydrogen is all over the place. But in order for that reaction to go off, there's a really big activation energy. And so you got to put in tons of energy to get this to go forward. And it's to the point where we have got this reaction to happen here on Earth. We have created scenarios where we can fuse hydrogen, but we have to put in so much energy to get that to go off that it's hard for us to contain it. It's hard for us to control that because we have put in so much energy. So what we do whenever we need to set this off, like get this to happen, we actually do a fission reaction. So we take uranium, which is easy to set off, and that releases a bunch of energy. And if we pack that with hydrogens around it, then the energy released from the uranium, like the nuclear bomb is what we've done, that energy is enough to get the hydrogens to start to react. And they release even more energy. But we have to set off a nuclear bomb to get this thing to happen. And so this is what's known as a hydrogen bomb. And that is more powerful than just a typical like nuclear bomb. And it's a fusion bomb versus a fission bomb. Technically, a fusion bomb is fission and fusion. Like we have to get the uranium to like release enough energy to set off the hydrogen. And so this is why all of our nuclear reactors that we get energy from in our environment, they all are pure fission, right? They're all just uranium. And that's because in order to get fusion to occur, that actually would give us way more energy. But in order to do this, we have to set off a nuclear bomb. And like we can't contain that, right? Like there's no building that we can set off a nuclear bomb inside and the building still be intact afterwards. And so you may have heard the term cold fusion, which is something that scientists around the world are trying to figure out. If there was a way for us to be able to do this fusion reaction by taking 2 hydrogens without having to set off a nuclear bomb, without having to put in tons of energy, if we could do this with less energy, aka cold, then all the energy problems of humanity would be solved in that case. We would be able to just like take hydrogen, which is all over the place. You take a breath, you just breathe in hydrogen. Like it's literally everywhere. We'll be able to take that and get a seemingly endless supply of energy. And I know that I said it's the most abundant element in the universe. Like if you look beyond like just Earth and like in the entire universe, I think hydrogen is something like 90% or 95% of the elements in the universe. So it's all over the place. If there was just some way that we could harness this and get this energy by smashing hydrogens together to produce helium, which is once again, the same thing that's happening in the sun.
Yeah. You know, you mentioned this, I think you mentioned it offhandedly at the beginning. You said something about politics. And if anyone is like me, you're like, what does that have anything to do with this? And I think this was something that I didn't realize until I actually started having conversations with my brother about this. The idea of like coal and carbon-based energy versus not carbon-based. And, anytime I would hear, oh, nuclear energy, it just sounded gross. It just sounded wrong. And it wasn't until I understood that, part of where some of this conversation comes into play is because when we have nuclear fission, we're not producing carbon. We don't have that kind of carbon footprint that, is so much in the media and in conversations about
gases
climate. Exactly. And if you think about it, right, based on everything we've been talking about, hopefully that makes sense, because fission, you're starting with something really big that is trying to get to iron. Doesn't get any smaller than iron, right? Mm-hmm. And so hopefully you can start piecing all of these things together, what we've been talking about, to see how they relate with one another and also how they have real world applications, and how understanding this can help someone have a more educated conversation on energy production, right? And knowing about cold fusion can help people get involved in the conversation. And it feels like this big black box, nuclear physics, but when you break it down, it's not too awful, right? And it's all about what's stable, what's not stable, energy, and also mass, and how we understand the discrepancies that we might find. And so that's where I can see the smile, because I know this is your jam. So you hinted at it a couple of podcast episodes ago, but this idea of mass defect that we need to know about, and the things that we've talked about, you're expected to understand for the purposes of the MCAT, as with basically everything we talk about on this MCAT podcast. But with mass defect, so knowing how much each proton, each neutron, what the atomic mass units are for those, we can predict what an atom should weigh, right? Or what a nucleus should, what its atomic mass should be. And that's not always what we get when we actually do the calculations and when we actually find out the mass of this atom. And so what can happen is sometimes our prediction is bigger than the actual value that we get. And so you should be asking yourself, well, why? And it's because this mass ends up getting converted to energy. Now, someone's going to be like, you are lying. Matter can neither be created nor destroyed. What is happening? What happened to conservation of energy? You don't know what you're talking about. For the most part, before, I did not, because I would have balked at the idea of this happening. But the reality is, if they're both changing at the same time, it works out. And we know that there is a relationship with mass and energy through equals MC squared. the equation that, like, I think you mentioned this not too long ago, everyone thinks they understand, but is like actually a little tougher to conceptualize when we really think about it. And so this defect is related to that nuclear binding energy that you were talking about earlier, Phil. And it's just, we don't understand that there is a discrepancy until we take energy into account and not just mass.
Yeah, this is super interesting. You're right. This is my jam. And this is the sort of thing that I get super excited about. It's really weird, because if you ask anyone on the street, like, what is the equation for mass defect? Like, nobody's going to say that. But if you ask anyone on the street, name any equation, E equals MC squared is probably going to be, if it's not the top answer, it's in the top 3, right? For sure. It's probably the most famous equation of all time, but also and so students know this, but they don't know what it's for. They don't understand what this equation is for. And you're right. Students are like, wait, conservation of mass, conservation of energy. And there's a good chance that you were told energy can't be created or destroyed. To be honest, I think I said that just a moment ago when I was talking about high energy to low energy, and it goes there. So where does that extra energy go? We can't create it or destroy it. Turns out we're all kind of lying a little bit when we say that energy can't be created or destroyed, or mass can't be created or destroyed. Technically, mass and energy can be converted back and forth into each other. You can convert mass into energy. You can convert energy into mass. And this takes nuclear reactions, and it's something really crazy here. But it understanding kind of mass defect and what does this mean? Through an actual example, looking through this, a proton weighs 1.007 AMUs, right? So a little bit more than 1. And a neutron weighs 1.008 AMUs. So a little bit more than 1. So protons and neutrons actually weigh both a little bit more than 1. So if I took 6 protons and 6 neutrons, that's 12 things total. That should weigh a little bit more than 12, right? It should be like 12.01 something or something like that, 12.0 something. But if you take 6 protons and 6 neutrons and you smash them together, what you have left, carbon 12, which we've talked about before, carbon 12 weighs exactly 12. I don't mean like 12 and some change. Like, no, it's exactly 12.00000000 forever, right? It's exactly 12. But the ingredients for it weigh more than 12. And so what happens in this case, if we take these individual like nucleons, the protons and neutrons, and smash them together, and when we put them together, it weighs less, right? What's happening is we're converting mass into energy, this nuclear binding energy to help kind of like hold the nucleus together. And this is some of the energy that happens when we release energy from like nuclear reactions. And the equation for this is E equals mc squared, where energy is E, mass is m, and c is the speed of light squared. Now, just for a moment, I want you to kind of think like if we were able to convert 1 kilogram of mass into energy, how much is that going to be? Well, m is 1, c is 3 times 10 to the 8th, and we got to square that, right? So it's going to be 9 times 10 to the 16th, aka 90 quadrillion joules of energy from burning 1 kilogram of mass and turning that into energy. That's a lot of energy, right? That's a ton of energy from just 1 kilogram. And so this is why nuclear reactions release so much energy, is because this conversion between mass and energy, it's a whole lot of energy that comes from just a little bit of mass. And this reaction is a super interesting one. And this is the idea of what's going on with mass defect. So note that in the sun, like we're actually losing mass of the sun because we're releasing that as energy into the universe outside of it. So every moment the sun is actually getting lighter. And I don't mean like brightness lighter. It's getting like ways less lighter because we're converting mass to energy. Now the sun's really freaking big. And so losing just a very little bit of mass doesn't change that much. But it is something worth kind of understanding. Mass defect is a term that the MCAT wants you to know as a student, something that they're going to hold you accountable for. And most students, like even a lot of students who have studied up until like test day, there's a lot of times I've come across students who don't know what mass defect is. It's one of those like kind of like weird things that, yeah, the MCAT does expect you to have some working knowledge of nuclear physics, which is a little bit tricky. This is not testable, but it's something super interesting. I don't know if you've read Azaii. Have you read The Martian by Andy Weir?
No, but no.
That was the movie with
what's his face? I think so, but definitely not the book.
Yeah. Oh man, now I can't remember that guy's name. Matt.
I'll find it for us.
Matt Damon. That's what it was.
Perfect.
Super good movie, super good book, because the guy who wrote that is very knowledgeable about physics. So he's one of my favorite authors because like a lot of the science in his books are actually like real science stuff, which is interesting. And so he wrote his second book, Artemis, was actually had to do with fiber optics and how they work. And then his third book, which was called Project Hail Mary, was about mass defect and about E equals mc squared. Super interesting book. Highly recommend it to any of our listeners. I realize this is not a book recommendation thing, but it's a really good book that goes like it's a novel, like it's fiction, but it's about evolutionary biology, like mass defect, nuclear physics, obviously like space travel and stuff. I think there's even some aliens. There are some aliens in it. So it's a super interesting, fun novel, but all of the science behind it is pretty interesting.
You know what? I don't mind a book recommendation every so often.
Yeah.
I'm hoping to get to a place where I can just sit down and read a random book.
Yeah. Skip the second one, read the third one. Artemis was not as good as Project Hail Mary. I have a
fiber
recommendation.
optics sounds more interesting to me because it's just playing with lights. So if anyone is like me and you are in need of a recap, because this was a lot, we're going to do like a very quick 30-second recap. And again, hopefully this made things easier and you don't want to split from our podcast. We care about you too much. When we talked about nuclear physics, right, this is just the study of the nucleus, the protons and the neutrons in them, excluding, right, everything else. We talked about the importance of stability and how nuclei seek that stability. And so for the most part, it's going to be fairly balanced on the smaller atoms. And then as you get larger, you need more neutrons to buffer all of these extra protons. Then we also talked about iron being very special, right? And everything ultimately wants to get to iron. So compared to iron, something like carbon is less stable, and compared to iron, something like uranium is less stable. And this allowed us to understand that the way that energy can be produced both from fission and fusion, even though one is causing the breakdown and the decay of an atom, right, an element, whereas the other one is bringing them together, fusing them together, and causing still the release of energy. So this is really counterintuitive that they both produce energy, but we're all coming back to, we want to get to iron. And then all the fun stuff about atomic bombs, hydrogen bombs, and how if we could just get a kilogram of not a kilogram of energy, a kilogram mass to be broken down and used for fusion energy would be what, 1 quadrillion? No, 9 quadrillion.
Or no, 90 quadrillion.
90 quadrillion, right? And then we also talked about mass defect, how you can go back and forth between mass and energy. If you're doing it at the same time, they're converting back and forth to one another using E equals MC squared. Now, this was a lot, but we want to hear from you guys. We want to hear, was this an interesting topic? Did it change your mind on nuclear physics? Or are you like, y'all, we need you to go back to the usual stuff? But also let us know what you want to hear about, what you want to learn about, because at the end of the day, we do this podcast for you guys. And as much as we love doing it, we want to make sure that you love listening to it. So we do have a podcast email here at Jack Westin, which we are both very stoked to finally have. And it's podcast@jackwestin.com. So send us your suggestions. We are stoked to hear them, especially as we move into a new year.